वाला बात नहीं करना, ठीक है? अमित सुनो तो भाई, सुनो ना, उसमें बोतल हो गई है प्लास्टिक की।
आवाज आ रही है मेरी?
हाँ
मेरा मोबाइल भी दो यार, अपनी अपना मोबाइल छोड़ के बाकी दोनों मोबाइल चाहिए। अरे यार मुझे लाइव देखना है।
स्टार्ट करने को उसका दे देना थोड़ी देर बाद।
लाइव हो चुका है तो इसका डिस्कशन होगा।
ओके, आ गया यूट्यूब पर सर।
कितना? डॉक्टर चितरंजन सर, अपना माइक चेक कर लें प्लीज।
नहीं करेंगे, लेआउट चेंज कर लेंगे। साइड वाली लाइन
स्पॉटलाइट में,
स्पॉटलाइट में तो आ जाता है, लेकिन स्पॉटलाइट में सिंगल आता है, आपको पिन करना पड़ेगा।
किस पर
आए जो बोलेगा उसको पिन करना पड़ेगा।
करते हैं
हमने इसको पिन किया।
आप बैठोगे यहाँ?
नहीं बैठूंगा।
यूनिवर्सिटी को बताते हैं यहाँ पर
करके यहाँ तो आवाज
ये तो बता दिया ना करना
नहीं सकता तो फिर वो बता देगा तो एक बार बात करते हैं क्या मतलब करते हैं कुछ नहीं आता।
हेलो,
गूगल मीट का करना कैसे अपनी?
नॉट ऑडिबल यस।
मैडम आपकी पहली कमाई भी तो होगी तो इससे
में बात करने वाले सब सुन काम करेंगे।
आपको नहीं चाहिए तो दे देना ना, आप लेने के लिए बैठे हैं, आप तो कल पार्टी दे देना, पैसे बांट देना, सब हो जाएगा। ड्यूटी तो देखो स्वयं को करनी पड़ेगी। ऐसे ही लोगों की आवश्यकता जिनको पैसे नहीं चाहिए, आओ आओ।
She has another source of income. She doesn't need that any type of loan. She doesn't need that.
सर को पता चल गया मैडम, आप रायपुर में कोचिंग ज्वाइन कर रहे थे, सैटरडे संडे की बात है।
She doesn't need. She doesn't need any type of money. Only
नहीं, ये छोटे छोटे नहीं चाहिए उनको, बढ़िया। आप तो एक काम करना, मैम कल ही दे देना हम लोगों को, मंडल पार्टी करते हैं, हैंड ओवर कर देना हम लोग को सर। 730 रुपये, 400 रुपये मिलेगा ये,
4 से 3.5
350, 700, 830 रुपये मिलेगा। शुरुआत स्टार्टअप तो वही चाहिए उसमें। पांडे सर, आप वो होस्ट के लिए वो केबिन बना हुआ है अपना, फुली एयर कंडीशन, साउंड प्रूफ, एक्सक्लूसिवली मेड फॉर होस्ट। हो गए, अब अपना सारा कब्जा अपना।
हेलो,
उसको बोलो ना जियो की सिम खरीद ले, नेटवर्क का इश्यू है उसके पास। देखो कैमरा ऑन कर रखा है, यहाँ दिख रहा है गोकुल सर, यहाँ दिख रहा है कैमरा ऑन कर रखा है, ऐसे ऑन कर रहे हैं।
हेलो,
उसमें नहीं दिख रहा, लेकिन आप वाले में क्यों नहीं दिखाया? दिखेगा दिखेगा, आप थोड़ी देर में देखना, आपको सब दिख जाएगा।
माइक ऑप्शन दिखा रहे हैं।
देखिए देखिए, अरे की पॉइंट तो बंदना बैठो, वैसे भी नोट करेंगे न्यूज़पेपर के लिए, न्यूज़ क्लिप के लिए। पूरा ही रिक्वेस्ट है चलो।
रिमूव करके देखिए सर उसको, ईयरफोन को। Yes, your voice was a little bit audible.
आपने कल अपनी वो मेडिकल लीव खत्म कर दी क्या मैडम? कल 3 दिन की? नहीं तो रखा रहता है ना। कितना बड़ा घर में वो छोटी तुम हो ना मैंने
हेलो
पांडे
Not audible.
अपने करना है पिछड़ रहा हूँ मैं इस बार पिछड़ गया हूँ इस बार नहीं एक बार भी नहीं सुनी आवाज़ एक बार भी नहीं सुनी आवाज़
You are not audible. You are still not audible. Yes, yes. Okay, okay. Yes, yes,
Okay, okay, thank
you are
you.
audible.
Okay, yeah. Okay.
Hello, hello.
Yeah, yeah. Just a minute. I have to set up meetings.
Yes, you are audible, sir.
हो गया, कर दिया शेयर। कुछ नहीं, आपको कुछ बताओ, समझ में नहीं आता। एडमिट करो, यहाँ से एडमिट हो रहे हैं, ऑटोमेटिक हो रहा है।
There was a connectivity problem. I request all the participants to be present.
Just a minute, give me. I'm trying to download my file.
Rangan sir, most welcome once again.
Yeah, thank you very much. I'm sorry for this interruption, and this is due to the technical glitch. So,
It's usual. We are going to start. Just wait for a while.
okay. So, shall we start or?
Kindly share your PPT, sir. I think we should check it before starting.
So, I have to share the presentation with you?
Both are possible. If you are able to
I
share
can.
yourself, or you may mail us.
क्या करना एडमिट सर पांडे सर
Rani ma'am, good morning.
तो बोलिए
Good morning.
Good afternoon, sir.
Very good afternoon, all of you. I would
I
like
think
to,
it's better I share my screen. Hello?
yeah,
Can you hear me, Mr. Beck?
yes,
Yeah.
please try
So,
to share it on your screen.
my screen visible now?
Yes, it is equal.
Okay.
Uh, Before starting, I request Vikas Kande sir to introduce them in a formal way. Uh, Kande sir, over to you.
Thank you, sir. A very good afternoon to everyone. I am Vikas Kande, Assistant Professor, Government Digvijay College, Rajnandgaon. On behalf of Department of Chemistry,
क्यों नहीं आ रहा? वहाँ पे यही मुश्किल हो रहा है। यही सीन मिलता है, यही तो है 14% मतलब 40 मेरे तो इससे मन कर रहा है मेरा इससे तो मन है अरे एक तो वो क्रॉस कर रखा है यहाँ पे डिस्प्ले इनपुट तो लेगा नहीं, इनपुट कैसे करेंगे? इसका आ जाए कितना इसमें आपको आ रही है इसमें नहीं आ तो बात करोगे कैप्चर ओपन करो क्लिक करो इसको नहीं नीचे आओ क्लिक कर लो डिफॉल्ट है क्लिक करो इसमें डबल माउस डिफॉल्ट तो होता है आउटपुट कैप्चर करो आउटपुट कहाँ से लेना तो सारे टूल्स हैं लेकिन टूल्स ऑन करो इसको क्रोम को भी ऑन करो सिस्टम का साउंड हटा दो यूजर क्यों नहीं चल रहा है यूजर क्यों नहीं इसमें इनपुट तो लगा ना आउटपुट नहीं दिखा रहा उसको नहीं और ना करेगा इसमें सेटिंग क्लिक करके हाँ बना हुआ मुझे बजट अभी वो आया था बच्चे चेक करो ओपन है नहीं मैं नहीं करूँगा मैं उनको प्रेस प्रेस में बैक होगी किती राहू यूट्यूब चल रहा है लेकिन उसमें वॉइस नहीं आ रहा है
फोटोज नहीं आ रहे थे फर्स्ट डे
फिर उसमें वो नहीं आ रहा था
मैसेज आ रहे थे इन्वेस्टमेंट करते हैं देरी हो 16
नहीं तो उसका बनना कैसे है
क्या प्लेटफॉर्म बनना है अभी तक
नहीं आ रहा है हमारे लगता नहीं वो यूट्यूब सामने लोग ऑन करके देखे तब तो समझ में आएगा
मैं देखूं
आप सब भी आ रहे हैं कैसे
मैं देखूं यूट्यूब ऑन करके
उसमें आवाज़ नहीं आ रही उसमें आवाज़ नहीं आ रही नहीं आ रहा ना ईयरफोन आवाज़ नहीं आ रही कुछ भी नहीं आ रही हाँ हमारी बात हो रही है सिस्टम से काम नहीं हो रही है सेटिंग इसमें भी कितनी रहती है आप लगा
मोबाइल यूज करते हैं आवाज़ करने के लिए
नहीं हमको गूगल मीट को कैप्चर करें ना गूगल मीट में तो आए ना उसके बाद
हाँ
देखेंगे आगे देखेंगे इंटरनल माइक
यूट्यूब में ऐसे वीडियो डालेंगे और बर्थडे कार्ड मिल जाएगा और करने को मेरे लिए नहीं आ रहा तो मैं तो
यूट्यूब में चेक करता हूँ कैसे लगे इसको इसमें हमेशा बच्चे की इसमें इससे बेटा इससे मीटिंग बढ़िया है सर
combination of all these things, or basically one can take in A combination of all these things, in B also combination of these two, in X combination of these three, or combination of one of these. And why this kind of follows and basically cannot see it just like but if you look at this in the present day, the efficiency is like 26%. 26.5% efficiency, which is very close to the silicon solar cells. And silicon solar cells took almost like half, half a century to develop from like very early stage to the present stage. But this technology, it took only like 10 years to come from like 2% to the 26%. Also, we have to consider, okay, we know all of these scientific things like in case of silicon and other things, and we are just adapting this to the technology part of this perovskite. So here is an example of like how an XP can be used to investigate this kind of materials, and here you can see, I can show you, this is the perovskite, it's brown color, it's a perovskite, and when you leave in the light and the air and the moisture condition, then it degrades and it's getting yellow. So what's happening? What's the problem? So what we did, we put this much, this one we study what's happening over the time.
ऑडियंस का ऊपर ऑडियंस देखो तो देखो हाँ तो बाहर से क्यों नहीं आ रहा इसका कैसे नहीं आ रहा है नहीं आ रही अभी हाँ अभी भी नहीं आ रही इसमें कहाँ आ रही है इसी में नहीं आ रहा ये आवाज़ क्या आ रही है लीड की आवाज़ नहीं आ रही उसमें कोई इशू नहीं सेटिंग को
What one can see is, and if someone brings you this material and say, okay, why I'm not getting the efficiency, okay, you can see, you can look at this and say probably it's degraded, or you have lots of amount of lead, that means metallic. When it's metallic, then it's conducting, and then it's not a semiconductor anymore. So these are the things that one can analyze with these things. So we also did some other things like when you put aluminum oxide by using ALD. So ALD is very low temperature process, like one can use at room temperature also. So that's why it's good for this kind of perovskite materials to protect against the oxygen or air in the water. And then we put a few layers of ALD, and then you can see over the time it's getting one without ALD is getting yellow, and the other with ALD is not getting yellow, so it's still keeping the black phase or the brown phase. And from here we can see, like here you can see, like this is nitrogen spectra of this material and nitrogen spectra of this one. So when it's without ALD, and you see the nitrogen equivalent, when we have a when you have a ALD and you do the same processing, then it's staying there. That means like you cover with a very thin layer, and that is not allowing your material to degrade. So again, it's only very few nanometers, since we can see the film below the ALD layer, aluminum oxide layer, then again only few nanometers. And this is the beauty of this experience, that only it measures the few nanometers. We don't know what's happening really on the bulk. Probably if we dig in the bulk, then we have like plenty of nitrogen. It's not on the surface anymore. So these are the outcomes. So another thing is that, like, most of the devices, you take any device, so it's taking up different layers, and you take a solar cell or transistor or whatever, so it is taking up different layers, and basically these layers are almost like consist of like 5 or 6 layers. So for these kind of solar cells, we have like 6 layers, sorry, 5 layers. 5 layers, like a glass with conducting metal oxides, then we call ETL and then perovskite, STL, and gold. This ETL is N-type semiconductor. This perovskite believed to be an intrinsic semiconductor, and this STL is a whole transporting layer. That means like it's a P-type semiconductor, and the gold is a metal. So basically, what happens? They react with each other. Most of us are chemists, I guess, and they react with each other, and that's the problem. If they don't react properly, then you don't get a good device, and if they react properly, then probably you get a good device nature. On the other hand, also there are some materials they cannot react properly. Then you have to, these materials are good, but they are not reacting properly. Then probably you have to do some engineering, that's called interface engineering. Then you can put some layer over here that this perovskite will not react with this layer, and ETL will not react with the interface layer. So that means like you are compromising with the sacrificial layer. So these things can be possible studying those things. So for example, what we did a study like, we have a perovskite layer, and then we just deposit layer by layer, that's called fold, layer by layer, a fold transporting layer, that's called spirometer, which is now etched, which is P-type semiconductor, and you can see it's from the carbon, when you keep on depositing, then its intensity increasing, and the nitrogen intensity here is decreasing, and so on. That iodine and lead intensity are decreasing. That means like we are not able to see iodine substrate anymore. This substrate has lead, iodine, carbon, and nitrogen. So that means like after putting like let's say 10 nanometer, I am not able to see it. And if I put more, then basically I don't see anything else other than the substrate. And the substrate has carbon and nitrogen, and they have different nitrogen. This perovskite has nitrogen, which is binding energy at 402.8, and but when you put spiro, this binding energy is at 400 400 electron volt. So this is the way we can separate. And depending, if you closely see this, the binding energy is also shifting, and this binding energy shifts gives you a band bending, and this band bending these band bendings are responsible for your device to function. Like if you if the electrons are, sorry, the holes are here, the holes can flow from here to here, but electrons cannot flow from here to here. So that means like only holes are going here and the electrons are going here. So in this case, like you incident light, photogenerated electron and holes pair are pumped here, and they are separated by this layer and another layer here. So that's why this is necessary. And if you have something like which is very similar to this, then it will not work. So this is how XPS helps us to understand the interface of the material. And also what one can do, like basically you don't need to do interface. You have this material, and what we did, we put light, and depending on it's in the dark, and then when you put light, then it shifts. Then from there, one can say, okay, you have a band bending or you don't have a band bending. Normally, you just see a one spectra. Okay, it's at this binding energy, we put light, then it shifts, and then from there you can say, okay, here is the band bending. And similarly, we found another group of material, so their band bending is at the back, not in the front. These are the sorry. So there are a few other examples like a sputtering. Like what we do in the case of sputtering, you sputter with a argon ion, and then you remove the material, and then you measure. For example, here we measure carbon, and then keep on sputtering, and then at some point we don't have any carbon. Similarly, here it was gold, like you can see the gold, and when we keep on sputtering, then gold is removed and the lead is visible. At some point lead is removed, only titanium is visible. So from here we can say, okay, what's the thickness of each layer and how they are behaving. For example, here we can see it's on the surface, it's somewhere in the middle of here, and it's on the back. On the back mostly it's titanium dioxide and so on. So we have some experiments also, like what we do, we make a cutting of these devices and we measure over here each layer, all these layers, and from there we can get the electronic properties of these materials and chemical and electronic properties. For example, this is a device that is gold, spiral, perovskite, and titanium dioxide, and here you can see when you measure here, that's the what I was telling about the imaging. Here you can get like gold, and you know this layer is mostly gold, and this layer is mostly lead, and this is mostly titanium dioxide. So from here we can say, okay, if not only lead, if you measure carbon and other things, then we see, okay, this is perovskite, and this is completely gold, and this is titanium dioxide, and so on. So this gives an information about what is what and how the image looks like. And also we did the similar things, and probably it's too much information to you. So what you do, we cut a solar cell. The solar cells are like few micrometer, and we cut it and we measure in different positions. And depending on the position, here you can see. Here you can see it's a gold, and the green area is gold, and the carbon is mostly present everywhere. And carbon is the one of the contamination. It's present everywhere, so you cannot get rid of it if you don't prepare your samples inside the battery. And you can see in this region only the lead, lead, bromine, iodine, chlorine, each has higher concentration, and other in other places it is low concentration. That means it shows that this is of perovskite, this is gold, this is titanium dioxide, and this is also another kind of titanium dioxide. So from here we can say, okay, we can see different parts, and from there you can say, okay, which element is present with. Here we found like it's combination of bromine and iodine, and here mostly bromine and iodine, and here it's higher amount of bromine. So this is something we can say, okay, what's happening over there. And also depending on the binding energy, we can say, okay, if it's the bending is upward or downward, and then you measure it, you know if your device is working or not working. Then you come to lab and change the interface and take this as your feedback and change the interface and check again. So this is a feedback loop that, okay, if it's working or not working, if it's working, why, if it's not working, why it's not working. So this is what one can do with the experiment. Again, the same example, like here we see, we measure in the dark. If you can see, we measure in the dark, it's over here. And when you put light, it shifts to higher binding energy. And this is approximately 0.6 electron volt, and this 0.6 electron volt is called open circuit potential. That means the difference between the one layer of perovskite or semiconductor and another layer of semiconductor. In this case, it's a perovskite and the whole transporting layer. And here you can see this is the open circuit potential. This is the voltage that you get in your solar cells. And then when you put light, it's equilibrium with each other, and that means like you are generating this amount of voltage to drag away your electrons and volts. So with this, I would like to conclude my talk, and then I would say like XPS. I hope I could give you some insight about the XPS, which is a advanced technology technique for analyzing the chemistry of the surface. Not only chemistry, also the electronic properties and elemental analysis, thickness, and so on. And this can be used to different powders and film forms, and so it can be also used to biology, to electronics, to space science, and everything. So with this, I would like to thank the organizer and my dear colleagues to give me an opportunity to discuss my work. Thank you very much.
Thank you, sir. Thank you so much. Is there any question? any participants and guest has any question, please ask.
Sir, may I ask a question? Uh,
Yes, please.
Yeah.
Please.
Sorry, sir, it was a very nice presentation. The fact is, you were not well. That's why I'm very sorry if I'm disturbing you in any case. But one question rising in my mind. You said the binding energy, the kinetic energy that we give, the extra energy is converted then after photoelectron spectroscopy. The work function
Mm-hmm.
is already there with the material, and
Yes.
the total energy gets converted into the kinetic energy and the work function of the metal. So how are you relating the energy with the property of the material? How can you relate, how are you relating this property, the kinetic energy, with the property of the material?
Yes. So it's as I said, like it's very empirical. So you let's say like give me an example and then I measure it. I cannot say directly if the properties is like that. So basically, I can say you okay. It's has this chemical property. And depending
Yes,
on
sir.
that chemical property, we can discuss, okay, maybe like let's say you are working on electrochemical water splitting, and then I give you, okay, this cobalt has like this amount of 3 plus states and this amount of 2 plus states. And like let's say you are giving me cobalt oxide. Basically, cobalt oxide is good for water oxidation.
Yes.
And then the synthesis, I get the material, and I don't know what's this material. Then I can study, okay, it has like cobalt 3 plus states and cobalt 2 plus states, and mostly I can say, okay, it has higher amount of cobalt 3 plus states on the surface and lower amount of cobalt 3 plus states on the bark. Then if we see the properties, okay, it's good for electrochemical water oxidation, then we can say, okay, this is the property we're looking for, and then we can correlate. It's not only one material. So we have to study it and make a data, sorry, a database, something like that. Otherwise, I cannot say like, okay, I get a material and then it should be functioning for X, Y, Z application. So this is not possible. So this is, I would say like, I would say like XPS just support the analysis of the person, like who is doing the studies of device physics or device chemistry and whatever. But on the other hand, let's say most of the chemist friends, they come, okay, they because the precursor is something different, like they have like XYZ concentration, and they believe that after the formation it should make also similar amount of in their materials. But when you do the measurement, you know it's not the same thing. Like you say, like take lead and lead sulfide and you mix it and then heat it and like make a solid reaction. But a person will extract, okay, I will shoot lead sulfide. Probably it's not lead sulfide, it's something else. So these things we can say.
Right, sir. Very nice information. Thank you so much, sir. So get
Thank
well
you very
soon.
much.
Thank you so much.
Is there any other question? Okay, I think there is no more question. So thank you, sir. Thank you so much for this most valuable session. In spite of being affected from COVID, you have delivered your lecture so enthusiastically. This will definitely improve our knowledge in the field of photoelectron spectroscopy in surface chemistry. You have explained very efficiently and briefly about the solar cell, perovskite cell, XPS sampling depth, and application ultra-thin film. This will definitely help to other researchers and participants. Once again, I would like to give our sincere thanks from Department of Chemistry to Dr. Chitranjan Das sir for this valuable lecture. I wish for your speedy recovery, sir. Thank you so much, sir. Thank you.
Thank you, sir. Thank you very much.
Thank you very much for your organization and giving me the opportunity to discuss these things, and looking forward to see you again at some point.
Okay.
Bye bye.
Okay.
Thank you, sir, so much. Thank you.
Thank you. Get well soon.
Now, Now, I would like to brief about the tomorrow's program. Tomorrow, our first guest is respected Dr. Suman Samoy sir, and he is going to deliver a lecture on supramolecular gel, the smart function materials. And our second guest is respected Dr. Balram Ambade sir, and he is going to deliver his lecture on atmospheric chemistry. So with this, I thank to everyone for your valuable time and support. Thank you. Thank you so much. Well, sorry. Uh, sir, tomorrow is off, so the next session will be day after tomorrow. Thank you, sir. Thank you. Thank you.